All right, so let's continue on with summations, and we'll move on to a little bit more complicated of an example. We worked with just standard summations already. We worked with an index of 1 moving up to 4, which is what this is. We also worked with an index of 1, or excuse me, maybe 3 moving up to 4. So, like that. But what I'd like to do is try to evaluate our first equation where the I is not just I, but I squared. And what this means is that we have 1 plus 2 plus 3, but each of those is squared. And by the way, we know that that's 9 plus 4 plus 1, so that will equal 14. But there's a shortcut for this one too. In the same way that the summation of I equals 1 to 4, we could just do 4 times 4 plus 1 over 2 and figure out the answer fairly easily. There's one for this one as well. But it's a lot more complicated, and this is what it is. I'll just give you the answer to start with. Up to some number would be n times n plus 1 times 2n plus 1 over 6. Which sounds absolutely insane. I mean, how can that possibly be worked out? And so I'll show you, and not only will I show you how it works, but I want to show you in such a way that hopefully by the end of this video it's actually intuitive. You actually understand why it works. And in order to do that, I'm going to be using Legos in the same way that I've done in previous videos. So let's start by just kind of imagining what the heck this is supposed to look like. And this is my interpretation. Again, this is 1, right? And 1 squared. This would be 2 squared. So this would be a total of 4. And this would be 3 squared on the bottom. Total of 3. So it makes this shape. And we're asked basically to figure out what the area of this is. That's what this is asking. What is from 1 to 3 if you square each of them and add them all up? And in the same way with the last one, how the shapes fit together perfectly, these shapes actually fit together perfectly if you take 3 of them. Let me show you how that works. First 2 are shaped together like that, and it has this kind of weird gap in the back. And the third one will fit right in there and leave this one piece that juts out on the top, which is interesting. What's even more interesting is you can split that top piece in half, and it'll make a really nice three-dimensional shape. So again, what did we do? We took 3 of the shapes that we care about, and when we put them together, they make a really nice shape. And so if we could just figure out what the dimensions of this shape are in terms of n, and then divide it by 3, we'd have our answer, right? So let's do that. This is 3. This is 4. And again, to figure that out, let's see if I can do this. This was our original shape, right? So we know that this side has to be 3. This side is the 3 plus the 1, so that's 4. And this side is the weird one. It's 3 and a half. So because we're going up to 3, we took 3 times 3 plus 1 times 3 and a half. And we're going to take that whole thing and we're going to divide it by 3. Okay, so we took 3 times 3 plus 1 times 3 and a half divided by 3, or 3 times 4 times 3 and a half divided by 3. And it would work the same way with smaller shapes. I don't have them built, but it's always going to work in such a way as to leave this extra piece on top here. And by the way, if we work this out, 3 times 4 is 12, times 3 and a half is 42, divided by 3, and that's 14. Okay, so that did work. But what's cool is that if we take this and we just call it n times n plus 1 times n plus 0.5 over 3, that would kind of model everything. If we had a shape with just 2, see if I can make it work here. Well, not really. But if I had a shape with just the 2, and I had 3 of them together, it would make the same shape, and it would leave us with one extra thing hanging out up top. In the shape, it would just be the 2, though. And I could cut it in half and make it flush on the top. And so algebraically, if I were to take this, and I don't like this 0.5, I could just multiply top and bottom by 2. Then I could just apply that 2 to the last portion of this equation here. Last expression, I guess. And I get 2n plus 1 and then over 6, which is, of course, that guy. So all this is asking me to do is to take the 3 times the 4, and then I'm just algebraically needing to times it by 2 to make it work, but that's equal to this. 3 times the 4 times the 3 and a half divided by 3. And I actually like this equation better, and I'll show you why in a future video. It relates more to integration. But all this is the area of a 3-dimensional rectangular shape divided by 3 to get the exact shape that we need. And by the way, I don't have enough Legos to do this, but if you had enough, and you could even imagine if you don't, imagine that I did the same thing twice. I could fit the other one, just flip it, and the extra piece on the other one would fit right in here and make it flush. And then I'd have another one of these guys on top. And that would take 6 of them. 1, 2, 3, and then 4, 5, 6. I'd have 6, which would make it n times n plus 1 times maybe 7 high, 2n plus 1, and I could divide that by 6 to get the shapes that I need. Because the whole point of this was to figure out what 1 plus 2 squared plus 3 squared is, right? So either way it would work. Okay, so hopefully this makes sense. Just to reiterate, the whole concept is I'm going to sum up 1 through 3, and I'm going to square each of those numbers. I'm going to get 14. And I could actually go through and figure that out for each and every one of them, or I could think of it in terms of the shape. That if I just take, no matter how big this is, it'll always fit together perfectly like that, and leave a perfect gap in the back for that, and leave me one sum on top, which I can always split in half to make a really nice rectangular shape, 3-dimensional shape. And this allows me to do really big summations, like what's the summation from an index of 1 up to 3,000, for I squared. And I could just take 3,000 times 3,001 times 3,000.5 and divide it by 3. Okay, hopefully this made sense.